All right, well, thank you everyone for joining. Um, Welcome everyone to the second session of our spring 2024 program for the Virtual Inter-University Symposium on Infrastructure Management, or VISIM. Today we have Amir Fard and Rahul presenting their work. Each presentation should be about 20 minutes long, after which we'll take questions from the audience, and people are welcome to speak their questions out loud or send them in using the chat feature. I would like to point out this meeting is being recorded and will be made available shortly after. Thank you all for joining. So for a quick introduction, our first speaker is Amir Fard. Amir is a PhD candidate in the Civil Engineering Department at Toronto Metropolitan University. He holds bachelor's and master's degrees in aerospace engineering from Sharif University of Technology. And under the supervision of Dr. Al-Luan, his research focuses on risk-informed infrastructure life cycle planning. And currently, he is working on developing a multi-agent deep reinforcement learning framework for adaptive inspection and maintenance plan optimization for infrastructure networks. Amir, please feel free to take control.
Yeah, thank you, Carl, for introduction. Hello, everyone. Let me share my screen. Okay, can you see my screen?
Yes.
Okay, perfect. Thank you. Hello, everyone. I'm Amir Fard, and I wanna for today presentation, I wanna present my latest research in developing hierarchical deep reinforcement learning framework for optimizing cross-asset budget allocation. How we can optimize the resources distribution among different asset classes. First, I want to give you a background of the problem and how that's important. First, we explore the problem statement and different pieces of the problem. Then I explain this developed framework for budget distribution optimization, and then we go over the case studies and the results. First, you're familiar with municipal asset management and the challenges of managing different assets. Asset management in municipalities are a very significant task because it's crucial for urban development and well-being of the residents. Usually municipalities have different types of assets, diverse types of assets, such as roads, network, sewers, bridges. Different departments are in charge of managing these assets and planning for the future years based on the conditions. So this poses some challenges because resources are limited, and if you take into account the current state of aging infrastructures, so and they have a different performance goals, different constraints and needs. So that's very difficult to manage and make a decision of the overall budget distribution in different departments. So currently there is no rigorous plan or basis for decision making that how much which department needs, and usually this decision of distributing budget is based on the previous performance of the department. If a department, for example, transportation department, can use the budget for the could use the budget of previous year, so they can get more budget. And if a department cannot use a budget, so they will give less budget for the next year. So there is no rigorous basis for decision making. for budget distribution. And here in this study, we want to develop a framework for adaptive budget allocation among different asset classes. And here, this framework is based on deep reinforcement learning. And this is a hierarchical approach that first distribute the budget between different classes, and then decide how you need to distribute that budget within each asset class among different segments. So since the asset classes are very diverse and each one has a unique needs and constraints and performance goals, so addressing this problem is very important to provide a basis for decision making. And then sometimes asset classes has different designated budget. They have their own budget resource, and sometimes they may have a shared budget that can use the budget based on their needs, and it's based on the manager that how distribute the budget between asset classes. Since we have a different optimization here, first we need to make a decision that how we can distribute between different classes, and then the next layer of decision making would be how we can optimize MRR activities for within each asset class. And there are this needs to be done through an integrated approach of these two levels, because the decisions of these two levels are dependent on each other, and we need to provide the integrated approach. So each department here, one of the challenges is each department needs to manage that allocated budget wisely. So because if you get a budget from the overall shared budget and you don't use it based on an optimized plan, it means you are wasting the budget, and also you're affecting the level of service of the other asset classes because you already use the shared budget, portion of shared budget. Sorry. So here, as I said, the research focus specifically in this study is to develop a multi-source budget allocation strategy, and we can make sure this distribution is fair regarding the overall objective of the whole system. And then also, if we need to make sure that the allocated budget is being distributed within each asset class based on the optimized plan. So if we can, in this way, we can make sure the overall decision process would be optimized. So let's explore the problem for a single network when we have just a single asset type. Consider we have for example, a network of assets. It could be a sewer network, could be a pavement network of a specific type. So for that specific network, we want to maximize the overall level of service of the network over a specific certain planning horizon. For example, we want to optimize the overall level of service of the network at the average level of service, and this average is a weighted average. For example, in a specific network, for example, in sewer network, each asset segment has its own weight. For example, for sewer, you can consider length. For a pavement, it could be based on the area, based on the replacement value of new asset of that pavement segment. So in general, you want to maximize the whole network level of service over a specific time, for example, 5 years or 10 years. And here you can see this is this overall level of service is a weighted average of anticipated condition or predicted conditions of asset I at the end of, for example, year 1, 2, and then since this is a both spatial average of the asset segments, and we have 2 dimensions for the average. And here for the predicted condition, we can have a stochastic deterioration model, or we can have a deterministic deterioration model. In each cases, the conditions of each asset would be a function of previous decisions. If you just consider that just one single year optimization, so the overall problem is a linear programming problem. But if you have more than 1 year, so since the decision in the last year would be depends on all the decisions or all the conditions of the decision of the previous year, so then it makes the overall problem, even for a single asset, nonlinear. So that's why even for a single asset, the challenges of optimizing network level of service, optimizing the MRR planning is significant. And there are different ways to solve such a problem. And since this is nonlinear, so you can go through for example, genetic algorithm to optimize MRL activities. So here you can transform the problem to a sequential decision making. So sequential decision making, you can formulate it as MDP problem, Markov decision process. At each step of decision making, consider you have a state, a state of the current situation of the network, and based on the current situation, you want to make a decision. So you call that decision as actions. So you have a final set of actions. So if you consider if you have just a single asset, that action space would be, for example, if you have 3 options, so your action space has 3 options. But if you have a network of assets, so you have a combinatorial optimization, and your action space and also this state space explodes. And then based on the action you take, based on the transition models, that this is a function of each action and could be a function of the state. So you transit to the next state, and based on this transition, you will get a reward. So this is the overall framework of a sequential decision making based on Markov decision process. And the goal in this sequential decision making is taking actions in such a way that you maximize the future cumulative reward. So then you can transfer the goal in this problem that to find a policy, to find the optimized policy that at each decision step gives you the maximum future cumulative reward. So you can formulate the total return as an accumulated reward, and this is a discounted accumulated reward of the future reward based on your actions and states. And then you can formulate the action value function. So this action value function would be a function of the current state and the action, and basically it gives you how much is a benefit of taking different action at that specific state. And then you can, in a RL reinforcement learning problem, you can, for finding the optimized policy, it is equivalent to finding the optimum action value function. That at each state, you can you see which action can give you the maximum cumulative future reward, and then you can take that action. So based on this deep reinforcement learning framework, we developed a hierarchical reinforcement learning framework that can integrate the two levels of decision making. The first level is when you have a budget, when you have a budget for the whole planning horizon, how much you need to give to the overall system. For example, you have different asset types, different asset classes, how much you need to allocate from the overall budget of the whole planning horizon to that specific year. And then after from that allocated annual budget, how much you need to allocate to different asset classes. For example, if you have 3 asset classes or 2 asset classes of pavement and sewer, so first you want to make a decision of how much you need to give to that specific year from the overall shared budget. And then from that annual allocated budget, how much you need to give to pavement, and then how much you need to give to a sewer system. And after that, in the next level, you need to make a decision that allocated that asset class specific allocated budget among the single assets within that specific class. So we have, in this way, we have 2 levels of decision making. In the first levels, we use a policy gradient method, and the actions are continuous. The continuous actions are the amount of budget for that year, and then from that specific allocated budget, again we have a continuous actions that which is the portion of allocating budget allocation for each asset classes. And in the next level, that we use a linear programming to optimize MRR activities of that specific year based on the allocated budget in the higher level. So this is a simple linear programming formulation based on 1-year planning to maximize the next year level of service for that specific asset class. And the budget constraints would be the allocated budget for that asset class in that year. So in this way, we can decouple the decision making and formulate the linear programming for asset class based on the specific constraints of the asset class, and also a specific objective and performance goals. And here we have a training phase that we iterate this this framework to in the next slide I'll show you how I mean to train the agent, train the reinforcement learning agent to optimize the budget allocations decision. Here is a overall flowchart of this framework. First, consider we have agent block and we have 2 different agents. The first agent that is in the first level is the budget planner. We call it a budget planner, and optimize the annual allocated budget for that specific year, and also from that annual allocated budget, what is the optimum optimal portion for each asset class. And then when we decide about the annual budgets of each asset class, we go to the next level, and this agent is the annual maintenance planner. So we do linear programming for each asset classes based on their specific objectives and constraints. And then we gather the information, the MR activities, decisions, then to calculate system level of service. And the system level of service is a weighted average. It could be based on different weights for example, how much each asset class is important to the and contributes to the overall or system or municipal level of service. And then you can calculate a reward based on that weighted average of level of service of each asset classes. And then, so based on the decisions that was made, MR activities in level 2, we translate the overall system, all the asset classes, and go to the next state. And then you can do this iterative process to train the agent. So this is a case study for a Canadian municipality payment network. Here we considered asset classes as different networks of the total payment network. Consider arterial, collector, and local networks as a different asset classes. So it could be also a completely different type of asset, for example, pavement and sewer, or here we have a subclasses, in this case, a study. You can consider it at different asset classes. So in this study, we have 3 different classes. And you see, for example, arterial road has more than 13,000 segments, collector more than 14,000, and local roads have more than 33,000 segments. And also here, a level of service is level of service metric is a pavement quality index with 0 to 10 scale. Here you can see the initial distributions of the conditions for each asset class, arterial, collector, and local. This distribution is a weighted distribution normalized by replacement value. Here, replacement value, we mean replacement value of a new asset. And you can consider it as a reconstruction cost also. And you see this is a heterogeneous network. So each single asset had its own condition and also its own treatment cost based on different options. In next slides, explain what is the deterioration models and treatments. Here you see they have different initial conditions. And here system, we mean the weighted average of the conditions of the all 3 networks. So here the system conditions initial level of service is 5.74. We consider a simple deterioration model. It's exponential decay with 2 parameters. And here each asset class had its own deterioration model. In this framework, even each segment can have its own deterioration model. But in this case, we just consider that asset classes has different deteriorations. Here, this is a typo for local segments. lambda is 0.001. Sorry, just let me share again. Sorry. Okay, excuse me. And here is the treatment effectiveness model. We have two options, rehabilitation and reconstruction. And if you consider also do nothing, that its transition model is the natural deterioration model. In total, we have three different methods. For each single asset, we can take three different decisions at each year. Do nothing, do rehabilitation, or do reconstruction. And this plot shows the effectiveness model, and the effectiveness is based on the current conditions for each asset. In this study, each single segment has its own treatment cost for rehabilitation and reconstruction. Here is the budget assumption for this case study. Each asset class has its own designated budget that is fixed over 5 years. For example, arterial network has an annual budget of $20 million. And for 5 years in total, it is $100 million. And it is fixed for each asset classes. So they have its own designated budget that they can use themselves. However, we consider a shared resource that is shared among all asset classes. And on average, this shared resource is $1 million per year. And in total, in 5 years, you have $500 million. And here we consider a 20% tolerance flexibility. So you can consider each year this shared budget can be from $80 million to $120 million. Here is the results. First, we consider in different cases, we consider different objective functions. The first case is maximize the overall level of service of the system for 5 years. And here you can see the budget allocations for each asset class at each year, and then what is the performance of level of service over the planning horizon. So you see the green line is for arterial, and you don't allocate budget because you just consider the overall to maximize the system level of service. And the budget allocation decision could be based on the system dynamics, and that's natural if you just consider the system level of service. For the sake of time, let's go directly to the next, just a case 3. And here, in this case, we did a trick that instead of just maximizing the level of service for reward, we just try to consider reward as the minimum of the improvement for each asset class. For example, calculate the improvement for each asset class at each year, and then consider the minimum of those 3 as the reward for that specific step. So here you can see a harmonized development, and this is the difference between this case. So you can see you're improving 3 asset classes level of service in a harmonic manner, and you can see the effects in the budget allocations and the changes in level of service. And here is the difference. For sure, if you just consider the compare just case 1 to and case 3, if you just consider to maximize the system level of service, you achieve a better level of service at the end of planning horizon. But the yellow line is for case 3, that is a harmonized development. So thank you for listening, and I'm with you if you have any questions. Sorry for the time. I believe I passed the time.
Yeah.
No,
Let's move on to the second presentation. Unfortunately, we don't have much time. It's better to try to keep to the schedule.
Thank
we'll
you.
move on to Rahul's presentation. For a brief introduction, Rahul is a second-year master's technology student in transportation engineering at the Indian Institute of Technology in Kanpur. He completed his bachelor's degree in civil engineering from Chandigarh University, Punjab in 2021. His thesis supervisor is Dr. Aditya Baduri, and he is here to talk about the pavement condition monitoring and his work. So, Rahul, please take it away.
Yeah, thank you, Carl. Just give me a second. So is this visible, sir?
It's visible, it's visible.
So yeah, hello everybody, and thank you for inviting me. It's a big moment for me. So my topic is quality assessment of payment condition monitoring data of an Indian highway. But his supervisor is Dr. Aditya Madhuri. So first we'll talk about payment management system. It's just a systematic approach used by transportation agencies to manage and maintain roads effectively. So it consists of data collection, analysis, decision making, performance model estimation for different maintenance section, and then efficient resource allocation and making decisions on whether to maintain the particular section of payment or not. And this PAMS contains some parameters like functional and or structural. For example, functional elements, they are just road user based elements that focuses on providing a safe, comfortable, and efficient driving user for road users. This includes roughness, resistance, roadside safety features, and all. And then there are structural elements that focuses more on pavement structure, its load-bearing capacity and stuff. And it includes rutting, pothole cracking, and all. And yeah, out of this, roughness is a widely used metric in evaluating a pavement condition in PMS. Roughness is just an index of for the level of payment serviceability. You can say it is just the undulations caused by driver uh, at while driving. And then IRI. Coming to IRI, IRI is a commonly used method for documenting payment roughness, and it quantifies the basically the just give me a second. Yeah, so it comprises a vertical deviation. So you can see just longitudinal undulations you can observe while driving or while working on that. So roughness consider that, and it is basically typically measured in whether it is meter per kilometer or inches per mile. And typically nowadays NSVs are used to find out IRA of a payment section. NSV as in network survey vehicle. So this uses the laser technology. So basically lasers are mounted over the surface, and after after certain difference, laser pops in and distance or undulation is marked. And so yeah, so as IRA estimation, there are certain measurement errors and which are observed in the literature as well. So it might be due to operational processes that can be a starting point issue or the path followed by the device and then the speed, whether it is maintained or not. So these kind of issues. calibration has been done or not. So, and then there is variation in profilers, whether it is DMI, distance measuring instrument, or the lasers or the GPS. And then there are basically payment condition anomalies that constitute bridge joints or structural joints present in that segment. And also there are incomplete maintenance record, as in if there is undocumented maintenance happen, so the trend of IRI will reverse its engineering and then will basically note it as an error only. So, and then there are strategies for basically mitigating the error in IRI. So one of them is number of runs. So if you increase the number of runs, so if the same NSV is working on one time versus it's working on like 5 runs, so then what happens is the latitudinal and the longitudinal shift is averaged out of the wheel path, and thus LTPP performs 5 runs on each pavement section, GPONG, that recommended. So he basically classified it into network level and project level. Project level, the distance is less. You have to just perform the quality assurance. And for network level, there's this curve, deterioration curves and present and future status of the condition that is noted. So that is done for the network level. So for network level, the distance is high. So he recommends 1 run for network level and 3 runs for project level. And in Indian roads, 1 run is covered till now. So there is a need to analyze the effect of number of runs so that we can quantify as to what can be, the final approach of as for the number of runs and what is its effect on repeatability. And also the second parameter that we are considering is segment length. So segment length, as in, because the longer the segment length, so you assume that the length is 10 meter or then it is 100 meter. So basically what happens in the localized effects gets reduced or gets averaged out on the longer run. So IRC recommends 100-meter length to be considered, and then there's a factory et al. That recommend 100-meter over 10-meter after performing some ANN modeling, and the LTPP data is analyzed on 0.1 mile segment. So it also depends on the units that country is considering into account. So hence there is a need to analyze the effect of segment length also on repeatability. So also then we'll come to impact of measurement error in spatiotemporal assessment. So we have this 60 kilometers stretch from NH44, and we have the IRA data after some period of time, like they collect the data after every 6 months. So we have the data with us, and then one would assume after a certain point of time, like after an interval, the IRI to be basically, IRI is if the roughness increases, the IRI increases, and after a period of time, you would imagine the road to be get more rougher, and then thus IRI should increase, and therefore the if we plot a delta IRI, so it should just be the positive curves only. It can be negative on the points if maintenance has happened. So that means there is a drop in IRI values, and thus delta IRI would be negative. But it should be, consistently. But what we observed on this stretch was at 10 meter this. So you can see that IRI difference is like, we can see the random shifts occurring, and the first plot is of 6 months and the second is of 18 months interval. And then we have done this on 100-meter as well. 100-meter, what happens is, so you can see most like all the points except one is between 0.5 to minus 0.5, and here it is like minus 10 to 10. So you can see that the variation, the intensity has reduced, but still the shifts can be observed, that it is negative and positive without any notice. So choice of segment length may also potentially influence the average RI and run-to-run variations. So we have this problem statement that will evaluate the variation in RI data collection as a function of both segment length and the number of runs being averaged. Actually, at the end, it is just a trade-off between the segment length and number of runs, because if you increase the number of runs, then the finance is getting increased, if you increase the segment length, you'll get a more repeatable data, but as compared to you, but you will don't not see the localized effect of that. Also, we'll assess the repeatability of NSVs and the potential factors affecting the performance, be it features of profilers like type of laser use, pitch, and speed limit of that, and the basic principle and calibration exercise done on that. And then there is presence of distresses. They also cause IRI to be high or low, and then path traced by a profiler. So based on this, an experiment was performed to account the repeatability of profilers in and influence of number of runs and segment length and variation in IRI values. So 12-kilometer stretch from NH44 was selected for the experiment, and out of this, also we have done this section marking thing to influence the variation cost due to the path followed. So we have basically used chalk at a particular distance over like 200-meter sections. 11 stretches were marked based on the different categories of roughness levels, and then we did the marking on them, so that the driver could see the marking and then try to be on the same particular path only. And we'll check the influence of this marking also later on in the in my presentation. And 3 profilers were used to calculate and analyze the RI data, and we have done 15 runs. So basically 15 runs were from these profilers were performed to check the averaging effect. And so, yeah, so these were the 3 profilers, device A, device B, device C. Basic difference is the type of laser used, because yeah, speed is also an important criteria, but speed we haven't seen in the literature, and also by our own experiment, the speed doesn't have much larger effects on the IRI values. So basically the differences are type of laser, whether be it a point laser or a line laser. Line laser, basically the pitch is high, also you can see in the pitch. So 2.5 centimeter for device A and 1 centimeter for device B, and then 1 mm for device C. So line laser is a continuous flow of value, so the pitch is very less. And for this device A and device B, after every 2.5 centimeter and 1 centimeter, the laser resonates a particular value. And also the time of the day for data collection is important, in the sense that we have done some marking whether they would be visual or not at the night time. So yeah, so 3 profilers were used. And yeah, so this is a picture from the experiment site. So basically this was just to perform the marking, and then the vehicle should run. And then these were the like chalk used for the certain point. So we have used it across the 200-meter sections. And then these are the 2 survey vehicles that were at the ground on daytime, and you can see a patrolling vehicle to basically to maintain the speed. And then we have one more device that works at night. So this is the visual that you can see at the night time. And finally, yeah, this is the team that works, so kudos to them. So data visualization, analyzing the effect of 10-meter and 100-meter. So for analyzing the 15, so we have 15 runs, we have 6 kilometer, and then we have created this box plot. So box plot, basically you can see each for each segment chainage point, there is one box that is representative of the 15 run values, and the array values that we come after that. And then we also created this 400 meters. The left one is for 10-meter use. So you can see that there is a variability, run-to-run variation from segment to segment. But at 100 meters, you can see the things cool down basically. And but yeah, spread is still non-uniform. So for result, we just used coefficient of variation as a metric to be used for the measure of repeatability. This is nothing, just the variability of a set of measurement relative to the mean, that is standard deviation divided by mean. So lower COV would indicate lower standard deviation, and thus repeatability would be high. So first, talking about the average across runs. So in the next slide, I'll show the 15 runs. They are partitioned into different groups. So for example, 15 groups of 1 run will represent, like we have just used 15 runs and average them. So that is basically 1. run. And then using the five groups of 3 runs basically tells that we had grouped the runs into three runs of 5, and then average of them and the total average. So that will just compromise, that will be the representative of if we would have to use 3 runs instead of 1 run, and so on. So we have done it for 1, 2, 3, 4, so and so. I'll show in the next. Also, curves are drawn to. Also, there is one important parameter, that number of paths to be considered. Like, is one line from a payment section enough to, indicate the complete roughness of a payment? And also, does it have to do anything to do with the repeatability also? Because the data points will increase. So we have also basically used the curves of us. Let me show the curve. So yeah. So you can see this curve. So basically our objective is to keep the shift as left as possible. So COV, the left rate gets, that says that it is more repeatable in nature. So we have used, so you can see the thinner lines. For almost all of them, they are rightwards. Thinner line represent only one path, whereas the thicker lines, they comprise of, average of 2 paths. And then you can see, as we increase from purple to blue, we are basically increasing the number of runs. So as you increase the number of runs, you will see that coefficient of variation decreases, and thus the repeatability increases. And the reason, as I told earlier, also could be because of some random lateral and longitudinal shifts. They can be smoothed out as the number of runs increases. Then we did it the same thing on 10 meter also. 10 meter also the similar result, but the curves seem to be more smoother. That is just because of more number of data points, like 10 times data points in at the 10 meter interval. So yeah, and then we'll just go to the averaging effects across segment length. So as the segment length increases, so this is a plot for segment length. You can see the from purple to black, we can basically see the if the length increases. So 20 meter, 40 meter, 80 meter, 160, 320, 500, and then 1 kilometer. So as you increase the segment length, so what will happen is the localized effects due to any joint or any pothole or so will reduce at a higher segment length or so. So basically, yeah. So we have also analyzed this by the data that segment length should be high to keep the repeatability high. So then, but this is just the COV. This is just standard deviation divided by mean. So it doesn't tell what is the relationship between the standard deviation and mean. Is the mean causing standard deviation COV to be less, or it's the standard deviation? So we have plotted the mean versus standard deviation. In the left side, you can see the 10 meter, and right side you can see for the 100 meter. Also, these graphs are, I have basically imported the device C only. I have device A and B with me also. The similar results are observed there as well. So you can see here that there is a mild correlation between average IRI and the standard deviation. That says due to high standard deviation could be either due to the average IRI being high. So at like the more the rougher the road gets, and we'll see the standard deviation to be high. So yeah, and then there is this, since we have used 3 devices, it's important for us to analyze 3 of them, like which, because they represent a profiler type and the conditions of that. So to analyze that, inter-devices IRI variation. So performance of devices related to each other has been analyzed using y equal to x plots. Now, basically, you will see that more points lie upside of the y equal to x line and upside. So that says that device C has a lesser mean as compared to device A. So basically, you can. So we would, if they would be similar, like 2 devices, then the points shall lie on the y equal to x line. So expected line is the red one. Yeah, and then we have done this on standard deviation as well. So standard deviation, you can see standard deviation also, device C is much, so you can see upper shift in the value. So you can say that device C has higher high standard deviation. Also, when we look at 100 meters, so you can see this is just the effect of increasing segment length. You can see this standard deviation goes low to a very high level. So segment length, so it poses more impact of segment length to be studied. And then this just because this was so much so this is not much visible, so we just zoomed it in to see the effect, and you can see more points on upside, and we didn't on the other two devices as well. So less standard deviation in devices C was, and this could be the potential difference between A, B, and C is the type of laser used, because that will reflect also the pitch. So the pitch is 1 mm for devices, so standard deviation is low for that. So as that parameter is also very important. So line lasers are recommended rather than point laser, and like pitch should be low for that. Coming back to the
Rahul,
market.
I apologize
Yes,
for
sir.
interrupting. I just want to give like a 2-minute warning so we have a time for a question or two at the end. So you have a couple minutes left. Is
Yeah,
that
yeah.
right?
Yeah. Okay. So we just have one parameter left, that is marked versus unmarked. So 1.6 kilometer. So as I mentioned, sections was marked. 1.6 kilometer was marked, and yeah, so this is just so basically in this plot I'm showing the left side it is 10 meter and right side it is 100 meter. So the red point at the red plot at the right side, you can see that is for the marked, and left side it is not much clear. So it appears that all of them are performing more or less the same COV. That is because of the high number of points. And at 100 meter you can observe some things. So this was just to show between 10 meter and 100. And now there were two impacts, like day and night impact on marked. So at night it might be possible that the lines were not visible to the driver. Then what was the impact of that? So yes, so here I have basically use this plot. So in the left side plot you can see that 0 to 4 you have the red point, the red curve is less observed, like it is just till 65%. And in the right side where device B is used, which was a day device, so then you can see up to 95%. So that is the effect of this the day night impact on marked and unmarked section. Also, then importance of pitch. So now we have used the both of the instrument that were measuring the RI on the day. So then you can see the left one, the device B. Device B which has a less pitch, like 1 centimeter pitch. So that is more repeatable. That has less COV. So as you can see, the pitch and the day-night effect is also important. So conclusion, it is evident that measurement errors present in the IRI data collection. Choice of number of runs is important considering the inspection objective, performing cost effective. And since each time you increase a certain number of run, then expenses gets multiplied by the same amount. So that way choice of number of runs is very important, and the choice of segment length is important to make management decisions, because you can analyze even a 1 kilometer data and you'll see all the things are looking good, but there underlies some localized effect which you will not observe. And also the properties of NSVs also influence the IRI variation. It's just not the payment only, the NSV vehicles, which pitch it is using and which speed it is working and what is the resolution, they are also important. And future scope, we will basically analyze the sources of high standard deviation points, whether it is joints or whether it is some cracking distresses or so. So yeah, that was my time. Thank you so much, guys.
Thank you so much, Rahul, for the presentation. When I open it up, I'd say we have time for at least one question. So please feel free to ask away.
I have a question, Rahul.
Yes, sir.
And so essentially, are these probes actively being used by agencies in India to collect condition data on some road segments? I mean, basically, was this inspired perhaps by some question that they had in terms of the repeatability of their data collection practices and so on?
So basically the problem started, so we were working with, so my thesis also, I would like to acknowledge Cube Highways. So this company basically came to us. So they in the starting, I show you the 10 meter issues, data issues, the trends. So we observe these trends and then we send to the company that these are the basically unknown errors that are coming in. And then the other companies which they were using for data collection and stuff, so they were also quite aware, and they were also like supportive in the way that yes, we want to find out what's the reason for this, and they also did not have any clear idea on this. So we basically then read the literature, and then that is how the process we have analyzed these results.
But Pablo, just to your question though, there are mandates to conduct periodic inspections given by the National Highway Authority. So they don't, oftentimes they give out assets, lease out assets for built operate, I mean, for toll operate transfer or annuity based incentives. So they have mandates to conduct these runs. And they essentially use it for some, coarser averages, that your average IRR of the entire corridor doesn't go below certain threshold. But there are a lot of data reliability issues. Nobody's using this data to do any form of performance modeling. So this company, for instance, interchangeably uses laser profilers, and the responses are just kind of all over the place. So until we looked at the literature, we also didn't realize that measurement errors might be, can be a big issue.
Any other question, guys?
I want to thank everyone for attending. And we are at about our time. And so thank you for both of the presentations and the questions, and for everyone attending. Hope to see you at our next session in the first week of May. Thank you all.
Thank you.
Thank you. Thank you, Amir. Thank you, Rahul.
Thank you.